Hi, Mr. Dorr. It's Charlie and Chloe, and we are going to be talking to you about GPS and relativity. So let's begin. So our table of contents, this is what we're going to be talking about. First, what is a GPS? What does relativity have to do with GPS? GPS's improvements over time, and how GPS has improved other fields of study.
To start, I'll go over what is a GPS. GPS is basically satellites that can be tracked from ground by measuring the frequency of the radio signals they emit. Conversely, the location of the receivers on the ground could be tracked by their distance from the satellites. Receivers in vehicles on the ground would derive a precise set of location coordinates by measuring the transmission times of a radio signal from satellites. GPS Global Positioning System. So there are 24 satellites in orbit. That guarantees a minimum of 4 satellites are visible anywhere on Earth at any given time. Satellite clocks are moving at 14,000 kilometers per hour. They circle the Earth twice per day. Some magnetics. Satellites are designed not to be magnetic so that they're not affected by Earth's magnetic field. Solar winds can affect satellites. Some winds are powerful enough to fry the satellite. Earth's magnetic field protects the satellite from solar winds by diverting charged particles. What does relativity have to do with GPS? Here's a quote from Einstein. When you sit with a nice girl for 2 hours, you think it's only 1 minute. But when you sit on a hot stove for a minute, you think it's 2 hours. That's relativity.
There's 2 general types of relativity, and they work in conjunction with one another. So there's special relativity, and that states that the speed of light is constant everywhere. But in order for this constancy to remain, space and time must undergo length contraction and time dilation. When an object moves at great speeds, it experiences time more slowly, and that's time dilation. And then there's general relativity, and that is the observed gravitational effect between masses that results from their warping of space-time. And it only applies when objects move at a constant speed, and it works in tandem with special relativity to justify time dilation experienced by satellites.
Einstein's theory of general relativity predicts that clocks in gravitational fields run slower compared to clocks not in gravitational field. And the stronger the gravitational field, the slower the clock runs. So if you look at the picture on the left, you can see that we have 2 clocks, A and B, at fixed points in space. Bob, the guy in blue, is holding his own clock and free fall in reference frame towards the Earth's surface. So according to equivalence principle, our preference frame is inertial, and therefore our clock can do good measures of time. Note that any other clock stationary relative to us at some other location is not necessarily good at measuring time, since the equivalence principle is only true locally. Thus, we will compare the rates of Earth clock to ours only when passed by them. And then Bob passed clock A, and it's moving slow relative to Bob's clock. Similar situation happens when Bob moves past clock B, since it is moving with respect to Bob. So Bob is free falling, so he will pass clock B with a faster speed than clock A. Thus, in his good inertial reference, we will conclude that clock B is running more slowly than clock A. Therefore, we complete the derivation of the fact that the clock in gravitational field runs slowly. So does that mean that clocks in GPS satellites run faster since they are in a lower gravitational field than clock on Earth?
Yes, actually, it does. Scientists realize that the error caused by clocks in satellites causes them to run 38 microseconds faster every day, and that accumulates. So that can cause a difference of up to 15 kilometers per day in the GPS's tracking of locations. And now I'll explain the physics behind them. What happens is that the time dilation due to special relativity happens when the observer in an inertial frame sees the clock moving relative to them as running slow. There's a set of equations that describe this phenomenon. What's important to take note of is that the t prime is the dilated time and the t without the prime is stationary time. Since the term with the velocity in it is rather complex, we simplify it just by representing it as gamma and then calculating it separately. We're going to do a calculation to see how this figure of 38 microseconds is obtained. First, doing the calculation for special relativity, we know that GPS satellites move at a speed of 3,874 meters per second relative to Earth. And if we input the values into that term with gamma, the result is pretty similar to a second on Earth, but it's shown that Earth's reference frame is 8.3 times 10 to the negative 11 seconds longer on a GPS satellite. So over the course of the day, this accumulates to be about 7.2 microseconds, which is a millionth of a second, behind the Earth receiver after 24 hours. And the imprecision of time can cause the positional data to become inaccurate, as we saw earlier. So the gravitational time dilation is given by this equation here, where the variables are spelled out, but the term above light that makes reference to gravitational potential difference. So using Newton's law of universal gravitation, we can rearrange the formulas so that it is customized to the satellites, and then this equation at the bottom of the screen is given. We will come up with this ratio of the time for the satellite to the time to the receiver on Earth, and it'll show that Earth's frame of reference is 5.2 times 10 to the negative 10 seconds shorter on a GPS satellite. So the GPS's time is going faster. If we multiply that times 24 hours, we will see that it is 45 microseconds ahead of the Earth receiver, whereas the other calculations showed that it was 7.2 microseconds behind. So we find the difference, and that gives us approximately 38 microseconds of difference, which is the figure we had talked about earlier. If you rearrange the speed formula and the speed of light, you can find the distance discrepancy, and that is as much as 11 kilometers.
The GPS improvements made over time. Did you know that GPS uses a clock that runs on uranium or rubidium? Atomic clocks. Scientists realize that if you shine lasers on atoms, they can cool them to temperatures only a millionth of a degree above absolute zero. That is really, really cold. And these cooled atoms act as pendulums, since the cold temperatures allow the natural frequency of the atom to be measured more accurately. And the natural resonance of atoms provide a steady tick of the atomic clock, and they will not lose more than a second in millions of years. Here's a little timeline. From 1949 to 1952, NIST announces the world's first atomic clock and produces its first accurate measurements. In 1955, NIST builds a clock using cesium beams. 1960 to 1993, NIST improved the atomic clock's accuracy. And in 1978 to 1985, atomic clocks were finally installed to Navstar's system, keeping the time within 1 second for 30 million years. So what is so special about the new generation of GPS orbiters? So they have atomic clocks, and the atomic clocks must deviate less than 4 nanoseconds from the perfect synchronization with other satellite clocks. New antenna and signal processors, the GPS orbiters send out new right circularly polarized radio signals towards the Earth's surface. And these radio signals are so faint, we need new signal processors to receive them.
So finally, how GPS has improved other fields of study. It's had multiple impacts, but one that's notable is meteorology. GPS has improved it significantly, and it's improved it by having ground-based GPS receivers that measure absolute atmospheric water vapor levels, which is more precise than technology that measures humidity. And the water vapor data taken with other observations such as pressure and temperature supports the improved accuracy of weather forecasting, climate monitoring, and meteorological research. And the impact of the GPS technology's accuracy is that storms are more predictable and appropriate precautions can be taken, especially for commercial airplanes and ships. It's also had a pretty big effect on satellite telemetry. So satellite telemetry is using satellites to track animal migration and behavior, and the GPS trackers provide very accurate data. It's important to several fields of study, such as ornithology, marine biology, and ethology, which is the study of animal behavior. Because GPS in conjunction with biotelemetry allows positional data to be combined with behavioral data, so heart rate and breathing, for example, and subsequent information provides helpful insights about animals' reaction to environmental stimuli. So migrational data from GPS tracking in turn aids conservation measures. For example, knowledge of the critical stopover sites for blue whale migration allows conservation efforts to be put in place for those areas. And GPS also benefits many researchers because it's freely accessible and it's also very accurate. GPS is also important to a few essential services. For example, there are first responders. So they use GPS to locate where calls are coming from, signal of the cell off the cell towers to locate where the call is coming from if the person is unable to give them the address. It's also helpful for navigation and it prevents people from getting lost, which is important. And also cell phone networks. They use the cell phone signal that is provided by the GPS and the cell towers together to triangulate location. GPS also has some important application in industries. So for example, finance and also horse racing. Because the GPS atomic clocks are so accurate, they can use it to establish very accurate transaction times to prevent fraud. And GPS can also be used in fitness, so like an Apple Watch that tracks your path when you run, or entertainment, so games like Pokemon Go or the geotagging feature on social media. So that's all. Thank you for listening. And that was a presentation about GPS and relativity.